All right, the last part of chapter 4 talks about relative motion. With physics, we always give you like a velocity. Let's say you're doing 11 meters per second. Well, technically, that means you're going with respect to something else. And all motion, as Einstein proved, was relative to some other motion, which is where his theory of relativity came from. Everything has to be measured relative to something else. There's no absolute reference frame that you can measure from. You're measuring with respect. Now, what we usually do is measure with respect to the Earth. So if I'm saying I'm going, 11.4 meters per second with respect to the Earth, that's my speed compared to what the Earth is. But you can imagine that you're measuring your speed compared to something else. So let's say you're driving in a car. So we're looking top down here. And you're going in a car and your velocity is like 60 miles per hour. Okay? And there's another car right here, and it's doing 50 miles per hour. Remember that 60 miles per hour is the measure of your velocity compared to the Earth. But if you think of it from this point of view of this car, compared to this car. So imagine you're in this car right here, and you're not moving. The Earth is just moving at you at 60 miles per hour. This car is then coming at you at a difference of 10 miles per hour. So you can imagine the Earth is coming by at 60 miles per hour, but this car is coming at you at 10 miles per hour. Remember, this is our reference plane, so we claim that it's not moving. Or, you could say, what if this car is not moving? If this car is not moving, it's our reference frame, the Earth is coming at it at 50 miles per hour, but then this car is coming up from behind at 10 miles per hour. All those are equivalent, and the physics works fine. All the equations, everything works the same no matter which one you pick as your reference frame. And so we have to be careful when we're doing things on figuring out what relative motion is. Sometimes it makes it easier to pick relative motion or the motion of an object instead of like the motion compared to the Earth. You say, let's compare this motion to another motion. It works out best, or the most time you see it, is like an airplane flying through the air. Because the airplane cares about is how much air is going over the wings, how fast that air is going over the wing. It does not care how fast it's going over the ground. So if you're flying your airplane and there's a strong wind, it can change completely what your ground speed is, but to fly, the air going over your wings still has to be the same amount. I built my own airplane, fly it still, and the wings, for it to fly, I have to be going about 60 miles an hour. But if I have a 20 mile an hour headwind, then really I only have to be going 40 miles per hour with respect to the ground to have enough air flowing over the wings to make me fly. So that's why airplanes also always land into the wind and take off into the wind. So their ground speed doesn't have to be as high because you're actually letting the wind help you. And so when the wind changes, they have to change around how they land the runways. So if the wind changes halfway through the day and they were all landing one direction, they have to change around and have them all land the other direction. All right, let's talk about relative motion. So I'm going to do an example here. So this is an example out of the book. It says you want to fly to Cleveland, which is 300 miles away from Chicago. So we're flying from Chicago to Cleveland. Chicago, Cleveland. And it's 300 miles. Okay. And the airplane can fly at 500 miles an hour. So in still air, your airplane flies at 500 miles per hour. Or we should say it flies at 500 miles per hour with respect to the air. But a north wind of 50 miles per hour is blowing the plane off course. North wind, remember, north is up. But a north wind means it's coming from the north. So there's a 50 mile per hour wind blowing this way. So if you were going to take off from Chicago to Cleveland, and it's a straight east flight, and go this way, by the time you got to Cleveland, the wind would have blown you off. You would have missed Cleveland. Thinking about swimming across a river, right? If I'm swimming across a river to get it directly across, I can't swim directly across. The current will push me down. So I have to actually swim up at an angle into it so that I end up at the same spot. same thing here. The airplane's got to fly at an angle up here so that when it gets to Cleveland, it'll be at Cleveland and not miss it. So that's what we want to find out, is we want to figure out what angle should the pilot fly. Well, what we do then is we say, okay, we're going to draw a triangle, but it's going to be a triangle of velocities. The wind is coming from the north at 50 miles per hour, and the plane is flying at 500 miles per hour. Okay? So what we need to do is just figure out what is this angle here. Notice that when I did this, this is my actual velocity with respect to the ground going here. I'm going to lose velocity, so even though the wind seems perpendicular to the direction I'm going, I'm still losing velocity because I have to aim into the wind a little bit so that I make it to the right direction. I have to aim up. So this is just simply a trig problem. This is opposite over hypotenuse, which is sine. So sine of theta is just equal to 50 over 500. Or theta is equal to the inverse sine of 50 over 500. Or in this case, you have to fly at an angle of 5.74 degrees north of east. Right? North of east. I have to angle it like that so that I get to Cleveland. Now you don't fly up and then the wind pushes you down. The wind's pushing you continuously, so you're going at a straight line. Your just plane is angled into the wind. And that gets you the angle. Now for pilots, remember, north is 0 degrees. This is 90 degrees. That's east. 180 is down here south. So what I really do is I have to fly an angle of, or a heading of 90 minus 5.74 degrees, or 84.26 degrees heading. And pilots have to calculate what that heading is before they even leave the ground, especially in the old days. Nowadays, it's not as big a deal because you have all these computers and stuff that tell you what to fly, and you just fly your GPS track. But in the old days, when all you had was a compass, you had to know what the winds were, you had to calculate this, you had to fly that heading if you were going to find the right place that you were going to get to. So that's basically how to do it. Now the biggest problem I have with students, or students make on this problem, is when they create this triangle of velocities here, they put their velocity down here. That is not right because that is not the direction the plane is going. Remember, your velocity is always the direction you're going. In this case, you're going this way, so the 500 miles per hour has to be in that direction. Don't put it down here, then you'll get it wrong. All right. So, and let's figure out, since we're here, let's figure out how long it takes you to get there. Well, to do that, we have to figure out the ground speed. So I have to figure out what this one is. Well, I can use Pythagorean theorem and say that, oh, this is C, this is A and B, right? So I'm just going to take C squared minus B squared is equal to A squared. Or A, I mean. So the square root of 500 squared minus 50 squared is equal to A, which is our ground velocity, which is 497 miles per hour. And then to calculate the time, you just take the velocity, the distance divided by the time. Remember that we're going to constant velocity. Distance is just velocity times time. So to figure out the time, it's just distance over velocity. In this case, 300 over 497. And you get it takes 0.604 hours. And the reality is for a plane going that fast, going 500 miles per hour, a 50 mile per hour wind only changes your time to get there by 4/1000ths of an hour. Or seconds, as a matter of fact, less than a minute. So it didn't change much how long it took to get there, but it did change the angle you had to fly. Now when these jets get up and they're flying at 500 miles per hour, they get up high in the atmosphere, they can get into the jet stream, and then you can have 100 mile per hour winds, and then it makes a big difference. And that's why pilots try to plan and say, oh, where's the winds? Where's the best winds? So if I'm flying to Europe, I try to catch the winds that are blowing to Europe, so I get up into the jet stream and let it push me, and I can get there over an hour faster than you can if you don't. And that's why it always takes longer to come back from Europe to United States than to go the other way, because you're fighting the winds most of the way.